5.3. We got 3 problems that were asked for here. It said change this, 32 said change this to rectangular. This is the radius, this is the cosine, this is the sine. So radius times the cosine is the x. So I just pull out my calculator and do 0.4 cosine of 200 degrees. Oop, mode, it's in degrees at 200. Nope. 0.4 cosine 200, and I get negative 0.378 for the x plus I, and I got to do 0.4 times the sine of 200. And I get plus I 0.136, and this is negative. Both of them are negative. Which makes sense. If I'm going 208 degrees, that's down here, and I'm going out 0.4, I'm going to have a little less in the cosine, 0.3, and much less in the sine because it's not down very far. There. Now, using de Moivre's theorem, find this to the fifth. Now, we could just type that in the calculator and give us the answer. In fact, let's just do that real quickly so you quit stressing about it. 1 minus I, second period, close parenthesis, to the fifth is minus 4 plus 4i. But I want you to use de Moivre's theorem, which says change this to polar. So the radius would be 1 squared plus minus 1 squared. So that's square root. So that's square root of 2. And if I'm going 1 and minus I, the angle is minus 45. So I'd have cosine minus 45 plus I sine negative 45. And to take it to the fifth, I take this to the fifth, and I multiply the angle times 5, and this one times 5. So the square root of 2 to the fifth would be square root of 2 times square root of 2 is 2, times square root of 2 times square root of 2 is another 2, times 2 square root of 2 would be 4 square roots of 2. Cosine of 45, the cosine doesn't care about the negative, but this is counted on the unit circle. 45 minus 45, 1, 2, 3, 4, 5 times. So the cosine there is minus square root of 2 over 2 plus I sine of there is plus square root of 2 over 2. And so if I take 4 square root of 2 times a minus square root of 2 divided by 2, the 4 divided by 2 is 2, and the square root of 2 times square root of 2 is 2. So actually 4 times 2 over 2 is 4. And minus, plus, and square root, and I got the same thing here, but I'm just going to get a positive this time because there's nothing there, 4 and an I. Now, typing that in the calculator was easier, but if you had to multiply this out, 1 minus I times 1 minus I times 1 minus I times 1 minus I times 1 minus I, that would be a pain. So this was a very useful theorem when you were trying to do something like that. And it's also very useful when you're trying to take the cube root, because there's actually 3 cube roots when you're doing complex. Now 1 plus I would be 1 plus I would be up here. 1 square root of 2 is the radius. So in polar form, 1 plus I is the square root of 2, and it's at cosine of 45 plus I sine of 45. But when you're doing roots, you want to put in plus multiples of 2 pi. Plus multiples of 2 pi. Because we're going to take this, the power, just like it did up here, the power went on this, and the power it goes times these. The 1/3 goes on this, so we got 2 to the 1/2, that's what the square root is, to the 1/3. So we have the 6th root of 2. We can work that out. But we got to divide this by 3. We've got to multiply it by 1/3. So it's divided by 3, divided by 3. So 45 divided by 3 is 15. So we have the cosine of 15 plus multiples of, this would be 360, 2 pi. 360 divided by 3 is 120. Plus I sine of the same thing. Okay. So our answer for this is going to be, well, we can use 15. 15 plus 120 is 135, and 15 plus 135 plus 120 is 255. So the exact cube roots are the square root of 6 over, the cube root is 2 cosine of 15 plus I sine of 15. Cube root of 2 times cosine of 15 plus I sine of 15. None of those are special angles. And I can type that in. Or the cube, 6th root of 2 cosine of 135. That is a special angle. And the 6th root of 2 times cosine of 255 plus I sine of 255. If I cube this, I will get 1 plus I. If I cube this, I'd get 1 plus I. If I cube this, I'd get 1 plus I. There are the 3 cube roots. I didn't change them back to rectangular, but close enough.